Okay, this video is to show you how to work the mastery or fourth level of the DC single node pair single loop tutorial. And these are problems that will require using the circuit editor in a new mode, which allows you to do what we call SOT variable transformations. So the first thing, of course, you would have to do would be to view the appropriate section of the tutorial, which you would do by clicking this button and going to the website. I've skipped that step here, but you wouldn't be allowed to do that until you've watched it. Then again, showing examples is a great idea, and again, these are multi-step things, and so it kind of shows you how you go through simplification steps, and then the goal is usually to get to current or voltage division or something very similar to that. That's really, in fact, to be honest, that's the goal of nearly all circuit analysis, is, if possible, to reduce your problems down to single node pair or single loop type, because those are the easiest things by far to solve. And now not all circuits can be reduced that way, but if they can, that's always the best method. That's why we teach you this approach first. Okay, so let's start a problem, and we'll try the first problem type. So if we look at this now, this is a problem that actually involves more than two nodes and more than two interior meshes. Therefore, it's not susceptible to either of the available types of analysis, which are single node pair or single loop. So we have to use the circuit editor. But if we say, all right, we could combine these two things in series, well, then that will make it a single node pair circuit. So that's all we're going to have to do here. So in this case, we are allowed to do a SOT variable transformation, but we don't need to do that here. So all we need to do is combine these two resistors in series. So 4 plus 6 is 10. And I could put that on either one, it doesn't matter. And change the other one to a short, and check that combination. And that is correct. And now we're done doing pretty much everything we need to do. We could process this further, but since I can already use a current divider formula, I'm not going to bother. So I'm just going to exit. And I'm going to use the single node pair now method, because it now only has two nodes since I combine those resistors. So first of all, I'm going to find the SOT branch current, because that's what I need. And so I'm going to use one of these different types of terms. I think I'll pick a different one than I did previously, so let's use this term. And so we have 9 amps that's being divided from the source, and that's being split up between the 1 ohm and the 10 ohm. And of course we know most of it will go through where? Well, the smaller resistance, right? The 1 ohm. So most of the current's going to go here, a little bit will go through the 10 ohm. So when I'm using this form, as opposed to say this form, now I use the resistor of interest, because these are basically conductances here, the 1 over the resistance. So this will be 1 over 1, okay, and then this will be 1, and then this would be the 10. And that will give me the current through the 1 ohm resistor. Now I have to also check polarity. This 9 amps comes down here, and then it's going to go up there and over here, and therefore it is going to go in the same direction as I0. So I do have a plus sign in my equation here. So that is correct, and that's the only equation I really need here. And now I just need to numerically evaluate that using a calculator. We can see that that's going to be basically 1 over 1.1, or 0.9 roughly, times 9 is going to be about 8, something like that, 8.18 if we do it accurately with a calculator. And that's it. So again, you can always view a complete solution that's explained a little bit more in detail here if you'd like to do that. For the second problem type, this is going to be a little bit different now. So once again, it's a circuit that you say, well, if I could combine these two resistors in parallel, that would actually be a single loop circuit, and I could use the voltage divider formula. But the problem is I can't combine them in parallel, because then I would lose this current I0 that's flowing through only one of them. So that's where I need to do this idea called a SOT variable transformation, and that's discussed in the introductory tutorial, which hopefully you've already looked at. So now I'm going to go into Simplify Circuit in the circuit editor. I'm now in the pre-simplification with SOT variable transformation mode, which allows me to do that. So what I need to do basically is I'm going to change the SOT variable from a current to a voltage, because if I had a voltage here, then I would be able to combine those elements. So I'm going to create a new SOT voltage. You can call it maybe an auxiliary variable, and I'll select voltage label and polarity menu here. And I want to put a new SOT voltage with the plus sign on the top so that I have passive sign convention. Now you don't have to do it that way, but that's probably easier. It avoids minus signs in the equations. So I'm going to create a SOT variable there, and it's now created a new SOT variable. I have to give it a name, so I'm going to call it v0, just a lowercase o there. And now I want to get rid of this current, so I'm going to right click again and change that to none, so I no longer have a current there. But in order to do that, it's going to make me write an equation for I0 in terms of the new variable v0. Otherwise, I would lose my I0 and wouldn't be able to calculate it. And of course, that's what we're after, is the I0. So it's going to basically now put me back into the circuit editor in the middle of editing here. And I write a little equation for that. I say I0 equals, I have to use an Ohm's law formula, and I'll express it in terms of my new variable v0. So I'm basically expressing the new variable, or the old variable rather, in terms of the new one. So that's going to be v0 divided by 9 ohms. Now notice that I chose passive sign convention with I0 going into the plus side of v0, so I'd have a plus sign here. If I had, on the other hand, chosen the active sign convention, which would be the other polarity of v0, then I would have to have a minus sign. So I check that, and that is indeed correct, and it tells me just press no more equations. That's all I need to do there. And now I'm back in the circuit editor, and now I don't have that SOT current, so I can't actually combine these two things in parallel because that won't affect the voltage v0 because it appears actually across both of these resistors. Therefore, they can be combined. And so I take the product over the sum, which would be 72 divided by 17, and that turns out to be 4.24 ohms. Then I will click on this one to delete it and press the delete key, or again, I could do it here if I want. And now I check that combination. And again, if you forget what you were doing and get mixed up, you can always restore the circuit. I won't do that here, but you could. And of course, they also have the help and the video help over here. And that's correct. And by the way, the help now will actually explain the things you need to do when you're doing SOT variable transformations, which is a little bit more complicated than if you're just doing simplifications. And so it explains all of that down here. And like I said, maybe the video is easier for you because it's certainly less wordy, or I hope it is. But okay, so now we're done. We have a single loop circuit. So we'll exit the circuit editor. Again, don't close that close box or you would lose all your edits. Okay, so now single loop. We select single loop method, and we want a voltage. So I'm going to select SOT branch voltage, the V0, and I can use the standard voltage divider formula now because I've reduced it down to a single loop circuit. That was the goal there of the simplification. So now I'm going to have a 3 volts of the source divided across these two resistors in series. So the resistor of interest will be the 4.24. And then, of course, I have 4.24 again. And then over here, it's going to be the 1 ohm. So remember that the 3 volts divided by basically the 5.24 is going to be the current that's flowing in this direction. Okay. And I check polarity again. The plus goes to the plus. The minus goes to the minus. So indeed, I do have a plus sign there. So that will be the correct answer. And that's enough equations. So now I just need to evaluate them. And first I have to evaluate V0, which I just do from this formula. And that would give me 2.43, just doing the numbers there on a calculator. And then I would take that number and substitute it back into here and back substitute to get I0, which was the thing I was actually originally interested in. So this V0 is sort of an auxiliary variable that we introduced in order to make it easier. And so we didn't have to go back then to the original circuit, which is another way of doing it, but it's a little less convenient, especially I think in a computer screen. So, so we check those answers now, and that is correct. And we're done. And again, you can get an explanation of the simplified circuit here if you need that. Now we'll do the third problem type. And this looks a little bit, if you think about it, like a current divider, except the problem is we need to combine these two resistors in series, but we can't actually do that because of this SOT voltage that we're after, the V0. Because we combine them in series, that voltage wouldn't be there anymore. So once again, we need to do a SOT variable transformation to make it possible to solve this problem using current division. So we're going to go into our circuit editor as it tells you to do. And now we want to combine these things in series, but before we can do that, we have to change the nature of this SOT variable. So I'm going to do that by first creating a SOT current. I want it to go left now, so that it'll be passive sign convention going into the positive side of the voltage. Although, again, you don't have to do that, but it's probably more convenient. And then I'm going to label it I0, since we haven't used that variable before in this problem. And then I'm going to get rid of that SOT voltage by changing that voltage label and polarity to none. Okay. And then it says to delete that, I do have to write an equation for the thing I'm deleting, namely the V0, in terms of the new variable I0. So it's going to take me once again into the circuit editor, I'm sorry, into the equation editor to do that. So V0 is now, I'm going to use Ohm's law to get that. And so basically that's going to be in terms of I0. That's a lowercase o, not a 0. And that times the 4 ohms. And again, passive sign convention, so I'm good with the plus sign there. And then no more equations, and I'm back in the circuit editor. And now I'm free to combine those things at will. Now, I don't want to combine the 4 ohm into the 1 ohm because then I'd have to move this SOT current down here so that it doesn't go away. So basically I'm just going to combine the 1 ohm into the 4 ohm and do it that way. You usually want to keep the element that has the SOT variable already. It just saves you extra steps of having to move the SOT variable, which you can do, but there's no real need to do that. So let's make that 5, and then we'll change this to a short and check that. And that is indeed correct. So we're done with that combination. And now it's a single node pair format, so we don't really need to simplify anymore. We could continue with that process, but I'm not going to here. So we'll be done editing. And now I'm going to use the single node pair approach, and we need a SOT current, so I'll select that. And my I0, let's use this form this time. So it's 1 amp divided, and now I have to have the other resistor when I'm using resistances. So that would be the 3 ohm divided by 3 plus 5. Consistent with the idea that the larger current goes through the smaller resistor. So actually less current is going to go through 5 ohm than 3 ohm in this case because it's the bigger resistor. So we check that. Oh, and I forgot to mention the polarity. It is consistent here. So the 1 amp is going to go in the direction of I0. That's why I had a plus sign and not a minus sign. Okay, and then I also, well, I'm actually done there. And so now I just need to compute the values for these things. So I start with computing I0 from this formula. So that's just going to be 3/8 basically, or 0.375. And then the V0 is that times 4. So that would be 12/8, or I guess that would be 1.5. So that's good. And we're all done there. And again, we can see the detailed solution here. Okay, so the fourth problem. This is once again something that looks vaguely like a current divider, except that we have too many nodes. And so we'd like to combine these resistors in series. But in this case, we want the power dissipated in the 4 ohm resistor. So again, that would prevent us from combining these things because then we'd lose that power. So that's where we're going to do SOT variable transformations once again. First of all, I'm just going to combine the 1 and the 7 ohms. There's nothing to prevent that. So I'll just make that a single 8 ohm resistor in series and change that to a short. And now, however, I need to check that combination before I do anything else. If I forget that, then it'll warn me. Okay, now I'm going to change this SOT power to a SOT current, because currents are the things that can be found when you're combining things in series, right? Because the current would be the same through both elements. So I'm going to right-click on that and add a SOT current. And I can choose either direction here, so let's just make it go to the left, I think. That'll make the current division formula easier. And that I'll call I0. And now we're going to get rid of that SOT power, so we'll change the type of SOT power to none. Okay, right now it's dissipated power. We're going to change it to none. And of course it tells me, well, I have to write an equation for the thing I'm removing, the SOT power, in terms of the new variable, which is the SOT current. So it'll put me into the equation editor again, and I say the dissipated power in the 4 ohm resistor is equal to, well, in terms of that current, it's going to be I0 squared times the 4 ohm resistance, which is the relevant resistance in which I'm dissipating that power. And so that's going to be correct. And of course, polarity is very simple for dissipated power. It's always positive for resistors. Oops, I'm sorry, already did that. So I click no more equations. And now I'm free to combine these two things because they share only a SOT current. So again, I'm going to bind 8 ohm into the 4 ohm because otherwise I would have to move this current up here in order to keep it, and that's just an extra step. So let's just do it this way. Make that 12 and make this a short, and that's good. And now I've simplified enough that it's a single node pair, so I can be done at that point. And I have this auxiliary equation that's carrying along to remember my original SOT variable. Okay, so now I do the single node pair analysis. I find my SOT current using the standard current divider formula. So I'll use this form again. So that's going to be 3 amps times the other resistor, the 8 ohm, divided by the sum of the two. So the 8 plus the 12. And let's see, that's going to indeed have a plus sign because the 3 amps, part of it's going to come down here, and then the greater part will come over here. So that will be correct with a plus sign. Always check the polarity. And then we're done. And now we just have to numerically evaluate things. And so the I naught, we just get from this formula, so that's 8 over 20 times 3. So that works out to be 1.2. And then we plug that into this equation, square the 1.2 multiplied by 4. That'll give us 5.76. And we check those numbers, and that's good. So now we've solved that problem. And as always, you can get the detailed explanation, at least of the simplified circuit. Now for the fifth problem type, we're going to have something a little bit different. So this is an interesting circuit. It's single loop, but we have both a current and a voltage source in series, which means, as you learn in the introductory tutorial, that the voltage source is actually redundant. In other words, the current source is actually fixing the current through that voltage source, and in fact, for that matter, through all the resistors. So I could basically just ignore the voltage source and just use, since I know I have 8 ohms going into here, I could just use Ohm's law. And that's a fine way to do it. I could also, if I want to, while it's not necessary, I could go into the circuit editor and simplify things. So I'll actually show you how you could do that just as a matter of interest, and you don't have to. This is actually what's called a current splittable circuit, which is because these elements are redundant. And so I could actually eliminate this by changing it to a short, and then I could eliminate this by changing it to a short, and I could eliminate this by changing it to a short, because all of those things are unnecessary. And it tells me, hey, I just correctly eliminated a set of elements that was removably current splittable with respect to the rest of the circuit due to that 8 ohm source. So now it's much simpler, but I didn't really have to do that either. So let's just kind of restore that circuit. Well, actually, that won't do anything now, but I can abort the editing and just do the original circuit because I didn't really need to do that. I could have done it, so it's a matter of taste. So now I'm going to solve for that SOT branch voltage, and really all I need is an Ohm's law type of thing. So I need 8 amps times the 1 ohm, because the 8 amps is forced to go through the 1 ohm, and you notice it does so with active sign convention because it's going into the minus side of the voltage, and so I need a minus sign here. And I could also just put the final answer by using this term and just put minus 8 volts, but let's do this. And then that's all I need. And so you just evaluate that, trivial math, and that's done. And it'll also explain to you about why that's redundant and so forth. And that's that problem. Now the last problem type here, this is a single node pair circuit, but it's again unusual in that you have both a voltage source and current sources. And you say, well, what's up with that? Well, that means basically that the current sources, and in fact this resistor too, are all redundant because their voltage is already fixed by the voltage source, and all they are going to do basically is to change the current coming out of this voltage source, which isn't going to really matter because this voltage source already fixes the voltage across this resistor because it's directly connected across it. So these other elements are basically irrelevant. So once again, we could go into the circuit editor and remove those other elements because they're what's called voltage splittable. So I'll actually do it this time. I'll just delete that. I'll delete that. I'll delete that. And it tells me, yep, those were all removably voltage splittable. And this time I'll just keep it for fun here. And now, but you know, it didn't really make any difference whether I did that or not because I can still write the equation. So we'll do this as a single node pair circuit and just write the equation for the SOT current. I naught equals, in this case, it's so easy, let's just do the math here. and we'll say that's going to be 8 divided by 4. That's going to be 2 amperes. And again, the current's actually going to be flowing this way from plus to minus, so I need a minus sign. And that's correct. And now I've already evaluated it, so I don't have to do the other step. And once again, you can get the detailed explanation here if you need that. And at the end, of course, you'll be asked to do a little survey. And we do ask you to make any comments that you would like to give. That's very helpful to us in improving the program, so please do give us some comments. Okay, that's it for the 4th level.